Okay, this is part 284, C3K1, line 22f1fa19c3k1 Borosilicate glass Lithium Aluminium Hydride LiAlH4 fuel 5G Wow Seti. That's the Wow Seti signal there. So I'm going to Google borosilicate glasses, and quotes from Wiki. Borosilicate glass is a type of glass with the main glass forming constituents silica and boron oxide. Borosilicate glasses are known for having very low coefficients of thermal expansion. So there's the math equation to go with that at 20 degrees, making them resistant to thermal shock more than any other common glass. Such glass is less subject to thermal stress and is commonly used for the construction of reagent bottles. Borosilicate glass is sold under such trade names as Simex, Pyrex, Scott, or Refmex. So lithium aluminium hydride from Wikipedia, and there's the formula for it, and that's what it looks like. And this is in powder form. So that's the other names that it's called. And it's just got some stuff here. The mass and everything. Melting point 150 degrees or 423 K. It's reactive, it decomposes. It's dangerous, flammable. It's related to aluminum, sodium. Okay, so lithium aluminium hydride, commonly abbreviated to La, or known as LiAlH, is an inorganic compound with the chemical formula LiAlH4. It was discovered by Feinholt, Bond, and Schlinger in 1947. This compound is used as a reducing agent in organic synthesis, especially for the reduction of esters, carboxylic acids, and amides. The solid is dangerously reactive towards water, releasing gaseous hydrogen, H2. Some related derivatives have been discussed for hydrogen storage. So again, this comes up with the hydrogen storage. There are several videos in line K of this video. There's a whole bunch, tons of them. Yeah, there's quite a few. I haven't numbered them all yet, but that gives you an idea there. See? Lots. At least over 10 of them. So LiAlH4, I don't know if that's an I or an L, I'm not sure. So that plus 4H2O plus LiOH plus AlOH3 plus 4H2, okay? This reaction provides a useful method to generate hydrogen in the laboratory. Aged air-exposed samples often appear white because they have absorbed enough moisture to generate a mixture of the white compounds lithium hydroxide and aluminum hydroxide. Here's the structure of it. Again, I want you to notice that these cells here, it's the square, and then there's things floating in the square circles. It's got 4 points, and it's got the triangles, and these shapes keep coming up with this UFO design thing. But see how they're floating in the middle here? So that's what it reminds me of anyways. The crystal structure of Li atoms are purple and AiH4 tehedra are tan. Both of these have come up several times in the law videos in relation to the structure of the UFO that you want to build, or spaceship thing that you want to build that looks like a UFO. So LiAlH crystallizes in the monoclinic space group P21 divided by C. The unit cell has the dimensions of. Okay, so that gives you your dimensions. Again, you can follow along with this on if you go to Wikipedia and Google it, you can find it there. And I should have separated this. In the structure, Li plus centers are surrounded by 5 AiH4 tehedra. The Li centers are bonded to 1 hydrogen atom from each of the surrounding tehedra, creating a bipyramid arrangement. Those are atoms. At high pressure, greater than 2.2 GA. Trying to put a space here, it's ridiculous. A phase transition may occur to give B to LiAlH. Okay, so there's a graph there which is hard to read. So X-ray powder diffraction pattern of as received LiAlH4. The asterisk designates an impurity, possibly LiCl. Preparation LaH was first prepared from the reaction between lithium hydride, which that's come up before, and aluminum chloride, that's come up before. I can't talk this morning, it was terrible. Sorry, it's early in the morning, I'm trying to start filming, and it's getting dark outside because of the rain, and I gotta get this done. So in addition to this method, the industrial synthesis entails the initial preparation of sodium aluminium hydride from the elements under high pressure and temperature. Na plus Al plus 2H2 is Na1H4. LiH is then prepared by a salt methylesis reaction according to that. Sounds like thunder out there. Which proceeds in a high yield of La. LiCl is removed by filtration from an ethereal solution of La, with subsequent precipitation of La to yield a product containing around 1% of that. So here's the solubility data. It's got solvent, diethyl ether, THF, monoglyme, diglyme, triglyme, tetraglyme, dioxide, dimethyl ether, and there's the numbers for it. Again, that's on Wikipedia. Solubility of LiAlH4, MOL divided by L, or /L, whatever you call it. La is soluble in many ethereal solutions, however it may spontaneously decompose due to the presence of catalytic impurities, though it appears to be more stable in tetrahydrofuran, THF. Thus THF is preferred over e.g. diethyl ether despite the lower solubility, and then there's thermodynamic data. And it says exothermic, endothermic, and endothermic heat flux. Temperature, so this is what it looks like. Differential scanning calorimetry of as received LiAlH4. Thermal decomposition. LaH is metastable at room temperature. During prolonged storage, it slowly decomposes to Li3aLH6 and LiH. This process can be accelerated by the presence of catalytic elements such as titanium, iron, or vanadium. And then it shows the temperature changes for it. Okay. Differential scanning calorimetry is of as received LiAlH4. When heated, LaH decomposes in a three-step reaction mechanism. And there's the 3 stages that it does. R1 is usually initiated by the melting of LaH in the temperature range of 150 to 170 degrees Celsius, immediately followed by decomposition into a solid Li3aLH6, although R1 is known to proceed below the melting point of LiAlH4 as well. At about 200 degrees, the Li3aLH6 decomposes into LiHR2 and Al, which subsequently convert into LiAl above 400 degrees R3. Reaction R1 is effectively irreversible. R3 is reversible with an equilibrium pressure of about 0.25 bar at 500 degrees Celsius. R1 and R2 can occur at room temperature with suitable catalysts. So here's the LiAlH4 graph, and it shows you what it does. And here's the volumetric density, gravimetric density graph. I have no idea what this is. Volumetric and gravimetric hydrogen storage densities of different hydrogen storage methods. And so it's doing a comparison then. Metal hydrides are represented with squares and complex hydrides with triangles. Okay? Metal and squares. Reported values for hydrides are excluding tank weight. Dole freedom card targets are including tank weight. So August 14th, 2012 is when I did the research. Today's 27th of August, 2012. My thoughts. The keywords using the LiAlH4 plus fuel formulas. So I'm going to mix the borosilicate glass plus the obsidian glass together for space elevator mirrors, creating the new formula. You're going to cross-reference Obsidian and Borosilicate to see if it comes up before anywhere in the well data. And then you can add thermal shock plus thermal stress plus borosilicate glass plus silica plus boron oxide. So we're going to Google the boron oxide, and we're going to add lithium. Well, whenever I have a word I'm not sure what it means, I put Google boron oxide. It is in another video, okay? So it is being explained. Everything that I say that I need to do gets done in that line of work, okay? So lithium aluminium hydride plus lithium 7, other keywords, cross-reference well data for lithium and make new formulas with it. Those are my little notes for myself. Cross-reference these keywords in well data, create new formulas, 14th August 2012. So of course the next set of videos are all going to be about boron oxide, borosilicate glass, hydrogen storage, lithium, and LiAlH4. Okay? So we'll go on to our next set of videos.